Welcome to the third lecture of week 10 of Math 320. This lecture, we will touch on some of the basic properties of differentiation. Most of these you have already internalized since your first calculus course. The emphasis, therefore, is not on the fact that such properties are available, but on the fact that they can be proven as direct consequences of the definition of differentiation. In this lecture, we will focus on a handful of rules, all of which can be proven thanks to the limits definition of the derivative. The material we will cover are presented on pages 225 through 227 of your textbook. Let's start. The first statement we will prove is that differentiability is stronger than continuity. More precisely, if a function is differentiable at a point C, then it must also be continuous at the same point C. If you think back to the examples given in the first lecture, the fact that the step function is not continuous at the origin means, by the contrapositive of this theorem, that the step function is also not differentiable at the origin. The proof is based on rewriting the limits using the limit definition of the derivatives. First, we can rewrite f of x for x not equal to c as f of c plus the quantity x minus c times f of x minus f of c divided by the quantity x minus c again. The fact that the two sides are equal can be checked very simply. It appears that we turned an expression that is simple into an expression that is complicated. But in fact, the idea is that the way we did the rewriting is so we can tie it into the limit definition of derivatives. Now, notice on the rewriting, the first term f of c is constant and independent of x. In the second term, the first factor, x minus c, is a continuous function that vanishes when x equals c. The second factor is the difference quotient, which, though it is not defined when x equals c, we know that has a limit as x approaches c. The limit being the derivative f prime of c. Based on what we learned 2 weeks ago about the arithmetic of limits, we have that the limit of products is the product of limits when the individual limits exist. So the limit of x minus c times the difference quotient evaluates to 0 times f prime of c, which equals 0. And so the limit of f of x as x approaches c is equal to f of c. And this final conclusion is precisely the definition of continuity at a point C. If you stare at this proof for a bit, you realize that it actually says a bit more. On line 4, since the limit of x minus c is 0, in order to conclude that the limit is 0, we do not actually need the full strength of the difference quotient having a converging limit. No, it is enough that we know the difference quotient is bounded. So this proof can also be used to show that functions that have bounded difference quotients are also continuous. This also means, by taking the contrapositive, that if a function were to be discontinuous at a point C, then the difference quotient must be unbounded as we take the limit of x approaching C, this being the only way that the limit in step 4 may return a non-zero number. Our second result of today is the fact that differentiation is linear. More precisely, we assume that f and g are functions both of which are differentiable at some point C on some open interval AB. We will take lambda and mu to be two real numbers. Our conclusion is that the function given by lambda f plus mu g is also differentiable with derivative equal to lambda times f prime plus mu times g prime evaluated at C. The proof of this fact is essentially one line long. We start by writing out the difference quotient. This has denominator x minus c and numerator lambda of f plus mu g of x minus lambda f of c minus mu g of c. Regrouping the numerator, we find that we can write the difference quotient as sum of lambda times the difference quotient for f plus mu times the difference quotient for g. Now, if we take the limit as x approaches c, the difference quotient for f converges, and the difference quotient for g converges. These are both due to f and g being differentiable at c by our hypothesis. And since we know based on what we learned about the arithmetic of limits, we conclude that the limit of the difference quotient for the function lambda f plus mu g must also converge to the sum of the limits. And this is what we wanted to prove. The third result today is the well-known product rule, which is also referred to as the Leibniz rule. The hypothesis for this result are that f and g are given functions, both of which are differentiable at some point c in the interval ab. Then, the conclusion is that the product function f times g is differentiable at c also, and the derivative is equal to f prime at c times g of c plus f of c times g prime of c. Again, this result should be familiar to all of you. The emphasis here is on the proof using the properties of limits. To start with, we use a very useful formula for decomposing the differences of products. When given f of x times g of x minus f of c times g of c, we can rewrite this using the add something and subtract something trick. We will first add f of c times g of x and then subtract the same term. After doing so, we can regroup so that it looks like the quantity f of x minus f of c times g of x plus f of c times the quantity g of x minus g of c. Take a minute to mentally verify that this decomposition is indeed valid. Using this decomposition, we can rewrite the difference quotient for the product function. The difference quotient of the product f times g is precisely f of x times g of x minus f of c times g of c all over x minus c. Using the decomposition in the first step, we can rewrite this as the sum of the difference quotient for f multiplied by g of x plus f of c times the difference quotient for g. Now, if we place limits onto these expressions, notice that the limits of the difference quotients exist since both f and g are differentiable at c. The number f of c in front of the second term is just a constant, so has no effect on the convergence. The expression g of x in the first term is itself convergent to g of c. This is because, as we discussed in the first result of this lecture, that any differentiable function is continuous. So, since we assume that g is differentiable at c, we know that g is also continuous to c, and hence the limit as x to c of g of x evaluates to g of c. Since for conversion limits, the limit of products is the product of limits, this proves exactly that the difference quotient for the function f times g has a limit, and the limit is exactly f prime of c times g of c plus f of c times g prime of c, as expected. Our final result for this lecture is the power rule, where the power is a positive integer. It says that the derivative of the polynomial f of x equals x to the power p, where p is a natural number, is given by f prime of x equals to p times x raised to the power p minus 1. The power rule can be derived from the product rule by induction, as shown in this proof. In step 1, we announce the proof by induction. The base case is p equals 1, since we are trying to prove the statement for all natural numbers p. In this case, x to the p is just x, and we have already computed the derivative of linear functions to know that f prime of x equals 1, in agreement with the result. For induction hypothesis, we will assume that we know for a given p the derivative of x to the p is indeed p times x to the power p minus 1. For the induction step, we wish to prove that the statement is also true for p plus 1. Setting g of x to be x to the power p plus 1, we can write it as f of x times x. If we apply the product rule to compute the derivative, we find that the derivative of g is equal to f prime times x plus f times the derivative of x, which is just 1. So this gives p times x to the p minus 1 times x plus x to the p, which add up to p plus 1 times x to the p. And so the statement holds for p that is 1 greater, and by induction, the power rule is true. Okay, that's the end of this lecture. The next and last lecture of this week, we will touch on something a bit trickier, the chain rule. See you then.